Hi, welcome to Dissolve Chemistry. Let us continue our discussion on this chemical kinetics. Till now we have used differential rate equation to bring the relationship between concentration and rate of the reaction. In the present video we will discuss how we can relate the rate of reaction in the integrated rate equation form, so that we will see for different ordered reaction. So we know that for a general reaction, A gives product. The rate of the reaction we are going to relate on the concentration of the reactant, small change in the concentration with the small change in time. So that is differential form of the rate equation we are going to use, A to the power x. So now how this rate we are going to determine? By instantaneous rate we are going to obtain, and that instantaneous rate generally obtained by drawing the tangent to the curve at a particular time at which you want to know the rate of the reaction. In all the cases or every time, it is not that easy or convenient to draw the tangent and get the rate of the reaction. So therefore, to avoid this difficulty, the differential rate equation is converted into integrated form. So by using this integrated rate equation, we can determine directly by obtaining the experimental values. We can directly determine the rate constant of the reaction, and we can check the rate of the reaction. So that we will do by integrated rate equation, and this integrated rate equation for different reaction it will be different. Means different ordered reaction will have different rate equations, and let us start with the integrated rate equation for zero order reaction. Integrated rate equation for zero order reaction. So now to derive the equation for zero order reaction, integrated rate equation, so therefore you consider a general reaction. A gives product. Now the initial concentration of this at time t is equal to 0, you can consider it as A0, and at time t is equal to t, so then you can consider its concentration as AT. So now the differential rate equation, how we give? dA by dt, change in concentration of the reactant with time is equal to minus k into a to the power 0, because already we have mentioned it is a zero order reaction, therefore x is equal to 0. So now what we have to do is just to reorganize this equation. Fine. So we will do like this. Alright. So taking same terms on the same side. dA by dt and minus k, a to the power 0 means 1 into 1 it will be. So the next what we will do, right, dA is equal to minus k into dt. So now integrating this equation, you call this equation as 1. Under the limits of concentration A0 to AT, and under the limits of time t is equal to 0 to t, time t. So therefore what we will be getting, see here, A0 to AT dA is equal to minus k is a constant, you take it out, and then we will be getting t is equal to 0 to t, so therefore dt. So now what we will get under these two limits means it will be turning into what? AT minus A0 upon integration we will get like this. AT minus A0 is equal to minus k into what? T minus 0. So that is nothing but t. So therefore AT minus A0 is equal to minus kt. So now what you do, if you want rate constant, you keep k as it is and t you bring on this side, and negative sign also we can bring, or multiply both sides with negative sign. So then the equation turns out to be what? A naught minus at divided by t, where A naught is what? Initial concentration of the reactant at time t is equal to 0, and At is concentration of the reactant at time t is equal to t. Okay, so this is how we are going to derive integrated rate equation for zero order reaction. Okay, I hope you have understood how integrated rate equation we are going to derive for zero order reaction. Coming video we will discuss regarding integrated rate equation for first order reaction. Thank you for watching, and please don't forget to subscribe our channel. Thank you.